Hi everybody, so we're going to continue on our discussion of Coulombs law as it applies to certain problems. The first three problems or four problems were pretty straightforward, Regents level, and it's a good introduction, just some subtleties. The next two problems are what you see more often in a multiple choice problem or even a free response. Same equation, it's just now we're going to involve more than two charges or a more subtle aspect of that. So let's just jump right into it and make sure you feel comfortable with it. So now I have three electrons, 1, 2, 3, and this is very often what you'll see, just point sources, electrons. And they're separated by a certain distance, and they're fixed in their position. They're not allowed to attract to each other, or in this case, be repelled by each other and move as a response. We'll worry about the dynamics of that later on. Okay, so they're separated by 4 nanometers each. So in essence, I've written 4 nanometers, right? There's R, and this is separated by R. And we want to know what is the net force on the electron furthest to the left, okay? So just for simplicity's sake, I'm going to call this 1, 2, and 3 so I keep track of them. So the idea is this electron is feeling a force from the second one and from the third one. They're both trying to repel it. So if I were to draw a force diagram on these electron number 1, I would have a force here, and I would call that the force on 1 due to 3. I did 3 because it's small, it's far away, it's small, and then I'd have a bigger one, F1, due to 2. And I determine those arrows because we know that like charges repel. I could similarly do a force diagram on the second electron or third electron, but I'm not interested in them. And so something implicit in those arrows I drew is the 2 does not interfere with 3's force. Even though 2 is found between 1 and 3, 2 does not interfere. So these forces act independent of each other. There's no, if you will, interaction because one of the electrons is in the middle of the two others. That's, I think, a conceptual sticking point that has arisen. Once we establish that there are these two forces, now I can apply Coulomb's law to sum them. So I see they're in the same direction. So my net force, right, sigma force on 1 is simply, again, equal to the force on 1 due to 2 plus the force on 1 due to 3. If one of the charges had been positive, then I might have to make a negative sign because of attraction. But anyway, now I can do Coulomb's law. And I'm going to do it I'm going to not do every little term. I'm going to use proportions. So I know both these F terms have a K in it. So I'm just going to pull that out. I'm not going to put it in each one. Okay, you certainly can do that if you want. So now I have the force on 1 due to 2. So what is that? It's a charge of both 1. So it's Q1 times Q2. Since they're the same thing, I can just call that Q squared, right? Since they're electrons, all the charges are the same. Divided by how far? Well, it's R units away. I'm not even going to worry about the 4. Let's just say it's R units away, and I'm going to square it because I have to square it. So that's how I can reduce the force on 1 due to 2. If you want to expand this all out, do so if it makes it clear for you. Now, the force due to 3. So 3 has a charge of Q, so does 1. So again, I have a Q squared there. I don't need to put the Q1, Q2, Q3. And the only thing different is its distance. So if this guy is R away, then 3 is 2R away. So I got to be careful with my parentheses. I'm going to put 2R, and I'm going to quantity squared. Okay, don't do the noob mistake of writing 2R squared, because you don't end up squaring the 2 in that case, which is wrong. Okay, so now I can simplify. So I've got K. In this term, I've still got Q over R squared. Here I'm going to have Q over 4R squared. So I'm just going to do the math in my head. The common denominator is 4. So that's basically 5/4 Q, Q squared over R squared. So I could put in the actual R that was given. I could put in the charge of an electron, which is 1 times 10 to the negative 1.6 times 10 to the negative 19th, and then I could multiply by K, but let's just leave it in this form, because really in the AP, that's all we really care about. Example 6. Similar problem, but more conceptual. Okay? And this is, again, one that I know students struggle at times. You got to conceptualize it. So I've got two charges. Now this time one is positive and one is negative, and they're not the same charge. This one has half the charge as that one. So I'm asking, is there a place, and they're just separated by some distance r, where could a third charge be, and it's a positive charge, such that the net force on it is 0? Okay, so in other words, if I put that positive Q here, will the contribution of the force from this guy and this guy cancel out? Well, the easiest way to approach this at first is with vectors, right? If I want to cancel out, I need two force arrows in opposite directions. The 6 is going to attract this. The 3 is going to repel it. Well, these two vectors can't cancel because they're not 180 degrees relative to one another. They're not in opposite directions. In fact, you should be able to reason out, and definitely reason this out yourself, it can't be anywhere above or below this line because the vectors can never be, there'll always be some horizontal component to it that doesn't cancel out. So if they're going to cancel out, they got to be somewhere on the line. So let's start in the middle. Let's choose some arbitrary spot. And this is a conceptual way you have to approach this problem before you worry about the math. So the 3 is, remember, this is a positive Q. The 3 is going to repel it, and the 6 is going to attract it. Well, those are acting in the same direction, so they can't possibly cancel. So there's no place between the two charges that can make a field 0 or have 0 force. Okay, let's try to the left. Let's see if that works. All right, so I'll just choose some spot there, my positive Q. Okay, let me just redraw that. Okay, what's the 3 going to do to it? It's going to repel it. Oh, wait a second. I'm going to... Yeah, I'll stick with that. So the 3 is going to repel it, and the 6 is going to attract it. Again, the fact that the 3 is between the 6 and our test charge here doesn't come into play. It's not blocking anything. Okay, good. I've got two arrows that are in opposite directions, so they can potentially cancel if I get the distance right. So now we have to ask ourselves, is there any way that our combination of Q times Q over R squared can give us two equal magnitudes that are in opposite directions? Well, 3 has a small q compared to the 6, but it's also closer. So a small charge can be compensated for a short distance. So it will work to the left of this. And I'll come back to the math in that. If I go to the right, the negative 6 will want to attract this, the positive 3 want to repel, so I get my directions correctly. But there's no position I can put this to the right such that the magnitudes can ever equal, because the 6 has two advantages. It has a bigger charge, and it has a closer distance. So that will always have a greater magnitude on this one than the 3, so there's no way you can ever have anything in that zone. All right, so think through that carefully. Make sure you make sense of that logic, because that's one of the keys here. Now, what I want to do is solve for some distance x. And I'm not going to actually solve it. I'm just going to set up the equation. Okay, so what do we understand? We have a distance r, and I want to figure out where this q is at some distance x. I want to figure out how would I solve for x. Okay, so basically what I want is the force on q due to the negative 3 to equal the force on q due to the positive 6 to equal each other, right? They're balanced, and they're equal, so I can set them equal. Okay, so how do I calculate the force on q due to the 3? Well, that would be k, q, absolute value, times negative 3, q, all over, how far apart are they? X squared. That's got to equal the force due to the 6 on that, which is k. So we see the k's are irrelevant. They're going to cancel out anyway. Q, in fact, the q's are going to cancel, and times negative, I'm sorry, this should have been a positive 3, not that it matters, times negative 6, absolute value, oh, sorry, I should put a q there, all over, well, if from here to here is r, and from here to here is x, that's going to be r plus x quantity squared. So I've got a mess right here. Let me just simplify it. So Up here, I've got the q's, little q's cancel, right? So I've got 3 over x squared equals 6. Again, the negative goes away because of the absolute value sign, over r plus x quantity squared. And then you can have fun trying to solve that. I believe you'd have to use a quadratic equation. Or maybe not. I'm not positive about that. But at the very least, be able to set it up like that. Okay, so you're going to see many more problems like this in different situations when we learn electric field and electric potential. So you want to feel comfortable with checking out conceptually 3 zones along the line and then determining which one will work before you work out the math.